do you know what the drilling per day cost is on a ultra deep water well? Anybody have an idea? Ballpark? It's like $2 million a day. Yeah. So I don't know. Maybe cooling the fluid costs $100,000 to cool the fluid significantly. Maybe not that much compared to $2 million. Right? So, anyway. So that, the effects of temperature can have effect on a small effect on breakouts. I mean, something that we should consider. Also, the anisotropy of the rock strength. So when we were talking about failure models and strength of rock, we at least qualitatively mentioned the effect that anisotropy can have. Anisotropy typically comes from weak bedding planes in the rock. Right? I mean, most rocks are sedimentary or laid down over time. And so there's almost ubiquitously some sort of direction that has a more significant strength than the other, especially when fractures are considered as an overall consideration of the strength of the rock. So on the left here, we see the teleview from Wellbore log. And if you remember before, from last time, where you had breakouts, just two breakouts on either side of the well, there was sort of very clear lines, just two lines, if you remember from the last time. Sort of very clear two lines in the teleview. But here, there's more like four. They're not quite as distinct as before. But through careful interpretation of that data, you can see a wellbore that looks like this. And it's a little bit hard, but you might idealize that as sort of, if the original wellbore is there, that you have two kind of lobes on each side. And each of those lobes correspond to these areas in the teleview, okay? And the mechanism for that, or the reason for that, has to do with, well, there's two mechanisms. One is just the same mechanism as before, that the stresses exceed the intact rock and you get breakouts. And so here what I've drawn, if you remember, well, not what I've drawn, what the figure from Zoback's book. So the lines here are meant to indicate lines of strength or weakness rather in the bedding plane. So in other words, the rock it has more strength in this direction than it does along those lines. Okay. And so and then the little arrows are meant to represent a direction of one of the principal stresses. So if you remember before, from the very first kind of figure from the last set of lecture slides, from the Kirsch solution, you had these kind of isolines of stress, right, that bend around the wellbore. Right? And so due to that, you'd get a lobe here and a lobe here associated with the normal mechanism of breakouts, and that the rock exceeds the stresses in those regions exceed the rock strength, okay? But along the other two lobes can be, the mechanism associated with those is that the angle between the principal stress direction and the angle of those faults in the bedding plane or weaknesses in the bedding plane, slip then gets activated. And so then these kind of secondary lobes are associated with the stresses associated with the activation of that slip, and that causes those to exceed the failure stress as well, okay? So that's sort of the mechanisms of why you'll see these lobed behavior in an anisotropic rock. Yeah.
What do you mean by activation of slip?
Well, if you recall from before spring break, well, right before the previous test, we went through all that stress resolution, right? So then we know what the normal and shear stress is on our fault. And then right before spring break, I think maybe the lecture right before, when there was only about 10 people here, we talked about, so before the previous test, all we were doing was resolving the stress. We didn't actually know if it would slip or not, right? And so then we talked about a criteria for slip in that last lecture before spring break, okay? And so if we resolve the stresses on those faults, then according to basically a friction law, which is Moore's law essentially, Moore-Coulomb law, then we can, and your homework assignment or your computer assignment that you have to do for next week, you're going to get to investigate this and plot it. And I think just the act of that will answer your question. The act of going through that exercise will answer your question. But anyway, then according to the stress resolved on the fault and the friction law, we can know if the fault will slip. Okay, so that's what I mean by activating. The stress is oriented with respect to the fault in such a way that it will slip, activate the fault. Right, so that's what I mean.